Construction of ultra-thin films with anomalous properties and potential industrial applications in magnetics and semiconductors has been ongoing for several years. Such structures could, in principle, be as thin as a single layer of atoms. Do we have such a thin film? Can we build one? And is it known what the limitations are? The answers are maybe, perhaps, and quite likely. A problem has been an inability to observe in detail this epitaxial growth, most particularly to uniquely interpret these pictures. While read technology reflects in some way the process, a unique interpretation is lacking. Most especially, we're unable to observe epitaxial growth in real time as it proceeds atom by atom. The study of growth in real time at the atomic level is critical toward understanding structure and properties of films at thicknesses of less than 30 angstroms, most particularly when the lattice is just a few angstroms thick. Recent developments, however, offer substantive clues as to the how of the crystalline growth. It entails the use of a supercomputer to simulate the epitaxial process. Using it, never-before-seen observations are possible, glimpses, which provide substantive clues for further research and development. What follows is a step-by-step progression through just such an observation, including preliminary conclusions. Supercomputer simulation using molecular dynamics allows us an understanding of epitaxial growth as it occurs in real time. The possibilities are endless. We can simulate sputtering, molecular beam epitaxy and ion beam deposition, the growth of semiconductors and metals, the effect of the environment, and substrate temperature and form. A temperature-controlled substrate is first built into the computer, and particles are made to impinge on it with a well-defined energy distribution. The particles interact among themselves with well-defined interatomic potentials. Metals are simulated using spherically symmetrical potentials, two-body interactions according to Lennard-Jones potentials. Semiconductors require the use of more complicated potentials, which include three-body interactions. Using a supercomputer, Newton's equation of motion is solved at every instant of time. Nature, of course, solves these equations without our help or that of a computer. It knows. At very low temperatures, Lennard-Jones particles, metals, grow in incomplete layers with a regular hexagonal arrangement in each layer. At any instant of time, a graph of particle density versus time shows a regular layered arrangement with incomplete layers. Note that sequential layers are less and less complete. The in-plane arrangement is crystalline with well-formed hexagonal patches, defects, and dislocations. The defects increase in size at higher and higher levels, the reason for the incomplete layers. This is in qualitative agreement with experiments. A monoatomic metal cannot be grown amorphous even at the lowest temperatures. The growth is into defected polycrystalline material. Now imagine the surface of a metal, copper for example, at room temperature. One might expect a quite static surface, but the finding is amazing. The atomic mobility is quite high, giving rise to a high level of activity. Because of this high mobility, the layers become completed, the reason for the high temperature needed for good epitaxy. An easy way to visualize this is by following the motion of a particle for some time, in this case, 200 picoseconds. Notice that close to the substrate, the particles sit comfortably in their equilibrium position. However, at the growing front, a major activity is occurring. A few layers from the surface, atoms are continuously being exchanged. For semiconductors, this behavior is different. Here, there is much less mobility at the growing front, which implies that semiconductor interfaces are perhaps easier to grow. Many more studies are needed, together with extensive systematics. We're trying out our first steps, but we need bigger computers, new methods, and much more work and struggle. A combination of experiments using novel devices such as molecular beam epitaxy and sputtering, together with powerful computers and extensive numerical simulation. Studies using supercomputers will bring us closer to a detailed understanding of epitaxial growth at the atomistic level.